Good morning. I'm Munir Tali, a PhD student from the National School of Engineering of Sfax, Tunisia. Will try to present to you my paper titled An Improved Multi-Image Steganography Model Based on Deep Convolutional Neural Network, done with Mr. Mohamed Othmani from University of Gafsa, Tunisia, and Madam Hela Latifi from the Research Group in Intelligent Machines, Sfax, Tunisia. Well, we can start with the plan for this presentation. So we have in the first section the introduction, then the second is the related work, the third one is the proposed model, the fourth shows the experimental results, and finally we have a conclusion. Let's begin with the introduction. In information security, steganography is an important technology. Steganography is a method for encoding secret data such as message, picture, or sound into a non-secret object such as image, sound, or text message, known as a cover object. All existing techniques have concentrated on finding either noisy region or low picture complement like edge, texture, and color in the cover image. We provide an improved steganography strategy for hiding 4 photos in one image in this research with the intention of transmitting the greatest concealed data with the least possible loss of the quality of the cover. In order to do this, we created a deep learning network that automatically selects the best characteristic from both the cover and hidden image, allowing us to integrate data. The convolutional neural network is the deep neural network of choice for us, since it's largely used nowadays in many domains, including security, object detection and tracking, medicine of neurological element, and also in monitoring people. For the related work that uses deep learning for the steganography of pictures, of several implementations, four are the most important to our research. First, hiding image in plain sight, deep steganography. Second, reversible image steganography schema based on unit structure. Third, steganocNN, image steganography with generalization ability based on convolutional neural network. Fourth, multi-image steganography using deep neural network. The first model is the Baluja model. This figure shows the system's three parts that makes up the entire system. Left, preparing the secret image. Center, the image on the cover is hiding. Right, the revealed network, which is simultaneously trained but it used by the receiver to uncover the secret picture. The limit of this model is that the networks were trained only on natural image found in the ImageNet challenge. Consequently, there are significant mistakes in the cover and hidden restoration when we use another type of image, though the secret image remains recognizable. This model establishes a standard for encoding single secret image. It does not, however, address multi-image steganography. A novel picture steganography method based on unit structure is proposed by Jian. This method compresses and distributes secret images and all available bytes on the cover image. Using a unit structured convolutional neural network, the cover image and the secret image are concatenated into a 6-channel tensor as an input to the hiding network. For the extraction network, the trained decoder network is used to extract the secret image existing in the Stegano image. This method has significant advantages in visual effects, but still cannot show the results of using more than one picture as a secret in the input of the model. This figure shows the extraction network. Guyan has developed a novel steganography convolutional neural network, steganocNN model, that successfully reconstructs two hidden pictures while resolving the issue of two images being contained in a carrier image. The results of this model show that the model has a certain degree of success, but only with two images as input. We do not have the result of more than two pictures as a secret. Abhishek used multi-image steganography to cancel 3 photos in a single cover photo. He included the ideas from Kruk and Baluja to achieve this. The limit of this method is resumed in the fact that when they increase the number of images The loss for all the values is projected to rise as the number of photos increases, as more image characteristics are buried in a single image. As a result, they will need to establish a limit of how many photos may be placed on the cover image to get acceptable results. In this part, we describe our steganography model, which consists of a generic encoder-decoder architecture based on deep learning. We aim to combine the model of Baluja with the pipeline of Kumar. The preparation network, hiding network, and the reveal network are the three components that make up the model. Our objective is to be able to encode data about the secrets images S1, S2, S3, and S4 into the cover image C, resulting in C prime. That's very similar to C, while still being able to decode data from C prime to produce the decoded secrets images S1 prime, S2 prime, S3 prime, and S4 prime that should resemble the secrets images most accurately. This figure shows the encoder composed of 2 layers in the preparation network and 5 layers in the hiding network. This figure shows the decoder composed of 5 layers. Now I will explain our experimental results. Tiny ImageNet Visual Recognition Challenge was the dataset we utilized. A random selection of photographs from each of the 200 classes makes up our training set. 50 photos are taken for each class throughout training, totaling 10,000 images for both training and assessment. On a workstation occupied with an NVIDIA GeForce 1650 Ti GPU card, our experimental complement and outcomes were achieved. This is the loss function used. The training has been performed for value of beta 1, beta 2, beta 3, and beta 4 equal to 1. This figure shows the consequences of covering a single cover picture with 4 hiding images. The encoder-decoder outputs are shown on the left side, while the input picture are shown on the center, and the difference between the cover and the secret are shown on the right. In terms of the quantitative analysis, our model's performance is evaluated on error per pixel and also gauged with metrics such as mean square error (MSE), peak signal to noise ratio (PSNR), absolute pixel, and structural similarity index (SSIM). According to this table, average MSE values are very close to 0, average PSNR is a high value, and average SSIM values are very near to 1. In this table, we have reported the comparative results of our proposed model against the Baluja image model, Duyan model, their new model Stigano CNN, and Abhishek model on the performance metrics SSIM and PSNR. These comparative results show that our model output a container with a visual appearance closer to the cover image. Not only the container image, but the secrets images revealed by our model are also good compared with the results of the other image models. As conclusion, in this work, a multi-image steganography method has been designed based on utilized CNN, convolutional neural network, and the main goal is to achieve improvement in some stego aspects, including visibility. Our implementation extended the single image steganography model proposed by the recent implementation. We relied heavily on visual perception for overall loss and did not experiment with various types of losses that could have been better suited for our model. The future work will be focused on the improvement of our model to increase the capacity with some tests using different data sets and testing over different methods of steganalysis. We can also modify the beta values. And finally, thank you.